Good evening, everyone. My name is Shang Li, and today I am pleased to give you a thorough introduction to a very important topic in the field of UAV obstacle avoidance. As they navigate through increasingly sophisticated indoor and outdoor environments, our unmanned aerial vehicles' ability to identify and avoid obstacles is essential to ensure that they safely integrate into our skies. I would like to explain the structure of our discussion today. This presentation will be divided into 4 parts. The first part is technical challenges in UAV obstacle avoidance. We will discuss the primary technical hurdles that the engineers and researchers face in giving UAVs the ability to sense and avoid obstacle autonomously. The second part is sensor technologies for obstacle detection. Here, we'll dive into 4 types of sensors that enable UAVs to perceive their surroundings. We'll compare their advantages, disadvantages, and applications ranges. The third part is trajectory planning strategies. In this part, we will look at how UAVs plan their flight path to avoid obstacles and the existing problems and current research results. The fourth part is the future research directions. We'll talk about where the field is headed, discussing the future research directions that will shape the evolution of autonomous obstacles avoidance for the UAVs. To set the context for our discussion, it's important to understand the breadth of applications for UAVs and the diversity of environments they must navigate. UAVs are used in a wide array of sectors, from military reconnaissance to civilian applications like agriculture, surveying, and package delivery. The ability to avoid obstacles is not just a technical challenge, but a key to unlocking the full potential of these versatile machines. My goal is to provide you with a comprehensive understanding of how UAVs are becoming more adept at avoiding obstacles and what challenges lies ahead in the existing field. Now let's talk about the technical challenges. The first one is the real-time processing demands. The real-time obstacle detection is a critical capability for UAVs operating in complex environments. This challenge involves several key aspects that need to be addressed to ensure effective autonomous navigation and safe operation. Here are the main components of this challenge. The first one is the high-speed data processing. UAVs need to process a vast amount of data in real time to detect obstacles promptly. The sensors on board the UAV generate a continuous stream of data that must be analyzed during the flight. The processing system must be capable of handling large volume of data without delay to provide immediate feedback for obstacle avoidance maneuvers. The second is the dynamic environmental adaptation. UAVs often operate in dynamic environments where obstacles can appear or move unexpectedly. The obstacle detection system must be able to adapt quickly to these changes without relying solely on pre-programmed flight paths or areas. This requires an advanced algorithms that can recognize new obstacles and calculate alternative routes during the flight. The third is integration with UAV systems. The obstacle detection system must integrate seamlessly with the UAV's flight control systems. Once an obstacle is detected, the system must quickly communicate this information to the flight control system, which then execute the necessary maneuvers to avoid a collision. This requires a high degree of coordination between the sensors, processing units, and the flight control systems. The second technical challenge I would like to talk about is the UAV obstacle avoidance in their accurate establishment of 3D coordinates for obstacles in the vehicle's flight path. The process is essential for autonomous navigation and safe flight, and it relays heavily on 2 key concepts: sensor fusion and dynamic environment adaptation. Sensor fusion is the process of combining data from multiple sensors to produce a more accurate and comprehensive understanding of the environment than any single sensors could provide. For UAVs, this often involves integrating data from various types of sensors such as LiDAR, RGB-D cameras, monocular and binocular cameras, inertial measurement units. By fusing data from these diverse sensors, the UAVs can create a more complete and accurate 3D map of this environment. This includes not only the location of obstacles, but also their shape and size, which can be vital information for planning a safe flight path. The second is dynamic environment adaptation. The environment in which a UAV operates is rarely static. Obstacles can move, weather conditions can change, and the UAV itself is in constant motion. Dynamic environmental adaptation is the ability of the UAV system to adjust to this changing condition in real time. The UAV must process sensors data continuously and rapidly to detect changes in the environment as they occur. By analyzing the movement of obstacles and other environmental factors, the UAV can predict how they will change in the near future and plan its flight path accordingly. The system should include feedback loops that allow it to correct its understanding of the environment based on the new data. If the UAV's initial assumptions about the environment are incorrect, these loops enable it to adjust its model and the flight path to minimize the risk of collision. The algorithms used for data processing and trajectory planning must be robust enough to handle the uncertainties and the variations inherent in dynamic environments. The third technical challenge I would like to talk about is heterogeneous UAV fleet coordination. As we consider the operation of multiple UAVs in the airspace, we encounter a new set of challenges that go beyond the capabilities of individual vehicles. Coordinating a heterogeneous fleet of UAVs, each potentially differing in size, capability, and mission objectives, requires sophisticated control mechanisms and may benefit from principles of swarm intelligence. Swarm intelligence, which draws inspiration from the collective behavior of social organisms, introduces its own set of challenges. One of the main challenges in swarm intelligence is synchronizing the actions of all UAVs in the fleet. In nature, swarms operate with a high degree of coordination, which is difficult to replicate artificially, especially when dealing with machines that have varying performance metrics. While decentralized control can increase the resilience of the swarm, it also introduces complexity in decision-making. Ensuring that each UAV makes decisions that benefit the collective while avoiding conflicts is a difficult balancing act. As UAV navigate shared airspace, conflicts in flight paths are inevitable. The fleet's control mechanisms must be able to adapt a flight path dynamically based on changing conditions, such as weather changes, obstacles, or shift in mission optics. And a swarm intelligence system must be robust enough to handle failures within the fleet. If one UAV fails, the system must be able to recognize and continue operating without significant disruption. Designing such fault-tolerant systems is a complex challenge. Now I'm going to talk about the sensors. The LiDAR, or light detection and ranging, is a crucial sensor for obstacle avoidance. It works by emitting laser pulses and measuring the time it takes for the light to reflect back from objects. LiDAR offers long-range, high accuracy, and works in various lighting conditions, making it an ideal sensor for UAVs. However, the cost, size, and weight of LiDAR system can be prohibitive for small UAVs. Rudesny's UAV LiDAR pod is an innovative solution that brings LiDAR technology to smaller UAVs, making it possible for them to benefit from this powerful sensor. Next up is the monocular cameras. These are lightweight, low cost, and offer high resolution, making them an attractive option for UAVs. However, they do have their drawbacks, such as dependence on lighting conditions and limited depth perception. Despite these limitations, monocular cameras can be used effectively in conjunction with other sensors to provide valuable visual data. The TETRAS LRIF XP550 thermal monocular is an example of how these cameras are being used in this field, providing thermal imaging capabilities that can enhance obstacle detection in low-wind conditions. The third sensor I would like to introduce is the binocular cameras. It offers stereo vision for depth perception and better obstacle detection. They work by capturing two slightly different images from slightly different viewpoints, which are then combined to create a 3D representation of the same. However, they come with their own set of challenges, such as complexity in processing and potential synchronization issues. The Higg-Robert at FHL-D45I binocular depth camera is a notable example in the category. It uses two cameras to capture high-resolution images and create a depth map, which can be used for precise obstacle detection and avoidance. And the fourth sensor I would like to introduce is the RGB-D cameras. The RGB-D cameras combine color information with depth data, offering real-time performance. They work by capturing both the color image and the depth information simultaneously, which allows for more accurate and efficient obstacle detection. However, they do have limitations, such as a limited range and susceptibility to reflective surfaces. The depth camera DM-RGBD-501 Alpha is a prime example of this technology. It uses an infrared projector and a depth sensor to capture both color and depth information, providing a comprehensive view of the environment that can be used for obstacle avoidance. Now let's talk about the trajectory planning strategies, which is referred to the algorithm. The first is hard constraint method. The hard constraint method is in trajectory planning is defined by the use of mathematical constraints to ensure that the planned path is both safe and feasible. These constraints are typically based on the UAV's dynamics and the special requirements to avoid collisions with obstacles. The method involves formulating the trajectory planning problem as an optimization problem where the goal is to find a path that minimizes some cost function while satisfying all the hard constraints. The Miller D algorithms, Richard C, Bray Alpha, Royal Ames algorithms belong to the category of hard constraint methods. The hard constraint methods offer several significant advantages. By using convex form functions, this method can ensure global optimization, providing a trajectory that is not only safe, but also optimal in terms of the chosen cost function, such as time, distance, and energy consumption. The hard constraints ensure that the UAV maintain a safe distance from obstacles at all times, which is critical for safe operation in complex environments. And it can adapt to varying flight conditions by adjusting the constraints in real time, allowing the UAV to respond to changes in its environment or mission requirements. The second trajectory planning strategy is gradient-based optimization. It uses the gradient information of a cost function to optimize the UAV's trajectory in real time. The cost function typically incorporates factors such as distance to obstacles, smoothness of the depth of the path, and adherence to the UAV's dynamic constraints. The method iteratively adjusts the trajectory based on the gradient of this cost function, steering the UAV away from obstacles and towards the goal. The method is computationally efficient and does not require a large amount of memory, making it suitable for real-time applications on UAVs with limited processing power and memory capacity. And it can quickly adapt to changes in the environment or flight conditions. If an obstacle appears abruptly, the method can almost instantly begin to adjust their trajectory to avoid it. As you can see on the right-hand bar chart, the green bar represents trajectory using gradient-based methods tend to be shorter than those planned with other methods, which can lead to faster mission completion times. As we look ahead to the future of UAV obstacle avoidance, several key research directions emerge. These are designed to address the current limitations and to push the boundaries of what's possible in terms of UAV autonomy and safety. Here are some of the key areas that researchers are focusing on. The multi-sensor fusion and integration. As we've discussed, sensor fusion is crucial for establishing a comprehensive understanding of the UAV's environment. Future research might explore new sensor technologies and more advanced fusion techniques that can provide even more accurate and robust environmental perception. This could include the integration of AI and machine learning to better interpret sensor data. Incorporating machine learning and AI can enable UAVs to learn from experience and adapt to new environments more effectively. Future research might focus on developing algorithms that can learn optimal trajectories based on past data and adjust strategies in real time based on environmental feedback. And one of the main challenges in UAV obstacle avoidance is the need for real-time processing. Future research should focus on developing more efficient algorithms and leveraging advances in computing hardware to handle the increasing complexity of real-time data processing and trajectory planning. For fleets of UAVs, research into swarm intelligence and cooperative control mechanisms will be vital. This includes developing algorithms that allow UAVs to operate more effectively as a team with improved communication and coordination. When we finish our presentation, it's obvious that the field of UAV obstacle avoidance is both complex and dynamic, and there has a lot of progress in sensor technology, trajectory planning, and fleet coordination. In summary, the journey towards fully autonomous UAVs capable of easily navigating complex environments is still ongoing. It requires a multidisciplinary approach, which includes knowledge from areas like robotics, computer vision, control systems, and artificial intelligence. The potential applications for UAV will only continue to expand, from commercial deliveries to search and rescue operations, as we continue to push the limits of what is possible. And so thank you for joining me in this exploration of UAV obstacle avoidance. I hope this presentation has given you useful information about the current situation and future prospects of this fascinating area. These are the references I searched from the internet, and thanks to the works of those authors. Okay, thank you all for your attention, and I'm happy to take any questions you may have or discuss any of the topics we have covered in the presentation.